guys, welcome to another chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at multi-component distillation using the shortcut method. So before we actually take a look at a working example here, the question we should ask is, what is the shortcut method? Well, in short, the shortcut method is basically a technique that is used to determine the number of stages, the reflux requirements, and the feed point location of a distillation column without using any software. Now, this method was originally designed for the separation columns of hydrocarbon systems within the petroleum refinery, so it's well suited for systems that use a significant number of components. Granted, you can use it for binary systems, but here we're going to look at it for multi-component. Now, these are basically hand calculations. That's what makes these so powerful, but you can use simple Excel sheets in order to fully automate them. Now, if that's something that you would like access to, leave a comment in the video, and I'll maybe look at adding in a downloadable spreadsheet for the shortcut method. But let me know in the comments if that's something that you're interested in. Now, the components that we're going to talk about here are the minimum number of stages, and essentially we're going to use the correlation that was first developed by Fensky in 1932. The full derivation has been done by Richardson in 2002, but the equation that we're going to use in its raw state is xi over xr to the subscript d. We have alpha I n to the power n min multiplied by this xi over xr subscript b. Now you might be asking, well, what do all these stand for? Well, the first thing is the xi over xr is basically the concentration ratio between any component I and your reference component. Then the alpha value is the average relative volatility of your component I. And then n min is the minimum number of stages for total reflux, which includes the reboiler. So from distillation design, you will know that the reboiler actually accounts for one of the stages within the design. So the n min here constitutes, it includes the reboiler. Now, after the simplification and mathematical adjustments, the final equation that you probably have seen and tend to use is this one here. So we have it in its logarithmic state in order to bring, because our n min is actually in a power. So in order to bring that down, we need to use the laws of logs. Now, the additional components here are, we have this thing of xlk and xhk. So the subscript lk stands for light key, and that is the light key concentration. So you'll have a heavy key and a light key, and that's obviously what the hk stands for, is the heavy key. So these are the two components that we use. Regardless of whether we have a multi-component system, we have to use two reference compounds, and we select these based on which one goes to the top of the column and which one goes to the bottom. Now, the next parameter that is important is the minimum reflux ratio, because in part the reflux ratio is basically the ratio for the amount of material that leaves the column versus the amount of material that's fed back into the column. Now, adjustments to this parameter will determine the purity, but have an impact on the number of stages required, and we'll see analysis on that in the full example. Now, there are two renditions of the reflux ratio equation that we will use. We have Colburn and Underwood. So the first one here is Colburn, which gives us basically a summation of the average relative volatility multiplied by the concentration in the distillate divided by the average relative volatility minus this theta value. And I'll come back to the theta value in just a second. And then that's going to be equal to R min plus 1. Now the other rendition of this is, rather than it be in the distillate product, it's inferring here now to the feed. So that's what this F stands for. Now the key distinction here is that when we have an F, we actually replace Q. We replace R min with Q. Now, if you've seen our other videos, more specifically the McCabe Thiele method for distillation design, you would come across these Q values. And the Q is basically how we represent the state of the feed coming into the column. So do we have saturated liquid? Do we have saturated vapor? Etc. And this Q line is integral to working out how many stages we're actually going to need. And I'll put a link in the description to that because that goes into basically the graphical means of modelling a distillation column. Here we're talking purely on calculations and mathematical models. Now, coming back to this theta value, theta is basically the root parameter of the equation, and this can only be found experimentally. So, or what you can do is an iterative process whereby we can make the equations equal to each other and solve for varying values of theta. Now, the final parameter here is the location of the feed point. And we can find this because this is important for when we actually want to reach our specified goals. And what I mean by that is if we want to achieve a specific concentration or purity of the product, then we can't just put the feed point in the center of the column, because depending on the number of stages that we have right away, and depending on the operating conditions, we may need more space in the rectifying section compared to the stripping section, or vice versa. And it's heavily based on the chemistry of the mixture. So that's something that you would need to bear in mind when you're designing your columns. And the equation that we're going to use, again, we're not going to derive these equations. That is well out with the scope of this tutorial. But here, this is the equation that we're going to use, and the nomenclature remains the same. It's all the same. The only additional thing here is the B and the D. These are the flow rates for the distillate and the bottom product, respectively. So if we take a look at a full working example here, and we're going to look at how to apply everything that we've just spoke about. So this will be a fully comprehensive example for you here. So what we have is a multi-component mixture is being sent to a butane and pentane splitter, and it has the following compositions. So we have propane, we have ibutane, we have N-butane, I-pentane, and N-pentane. And we have our respective flow rates for the feed, the distillate, and the bottom product. Now we're told our column operates at 8.3 bar, and we want to determine the minimum and the actual number of stages, the minimum reflux ratio, the feed point location when the reflux ratio is at 3, and we want to analyse the effect the reflux ratio has on the number of stages. So quite a lot to do, but this is the full shortcut method for distillation column design. So the first thing we'll tackle here is we need the relative volatilities of our components, because all we're really provided with is the operating conditions and the compositions of the feed, the bottom product, and the distillate. So the relative volatilities can be found using this small equation here, whereby we have K, which is for a reference compound, divided by K of the heavy key. So these are the volatilities for each component, and the ratio can be found by this equation. But in order to obtain these values, you have to use the Deprista chart, and the Deprista chart looks something like this. So we have our, now this is just a random line, this isn't part of the example just to show you how we would link these up. But you have several different types of hydrocarbons. There's different variants of the Distillation chart. But what you have here is your operating pressures and your operating temperatures. And what you would do is you would draw a line connecting the operating conditions, find the intersection of your given reference compound, and that will give you the relative volatility of your mixture. Now, from the Distillation chart, rather than going through it one by one, we'll just summarise the information that we have. Now, our temperature here is 65 degrees and our temperature is 120 degrees. That was part of the question. It wasn't in the initial part of the question, but it now is here. So that's the temperatures that we're operating at. Now, what we want is we want the values for the top product, the bottom product, and then we need the average. And the reason we need the average is because that's what alpha represents. Alpha is the average relative volatility. So now that we have these, we can now begin to populate our equation. So we can find the minimum number of stages. If we use this equation, we will substitute in the values. Now these values here, the 24, the 1, the 19 and the 1, these correspond to the original composition table. And what we need here is a relative volatility of the light key, which in this case would be N-butane. So N-butane is a light key and I-pentane is the heavy key. And you might ask the question, well, why is that? Well, that's the components that feature in all three of the streams. It features in the top, obviously the feed, and the bottom. So that's the selection criteria for your light and heavy keys. The light key is obviously the one that will go to the top of the column. The heavy key is the one that goes down to the bottom. So just keep that in mind. Now this tells us here that the minimum number of stages in order to achieve this desired separation would be 8.8. So that's the first part done. Now the second part is using the Underwood equation, we can now deduce the minimum reflux ratio. Because we've now found the minimum number of stages, now we need the minimum reflux ratio, i.e. what is the minimum amount of material that can leave and be returned to the column at the top in order for us to achieve these targets. So the first thing that we'll do is we'll take our equation, and the reason we're taking this one is because we know that the feed is coming in at its boiling point. And we can check that out by the temperatures. It's coming in at its boiling point, which means we have saturated vapor. Now that then infers that our Q line is equal to 1. So therefore, if we do 1 minus 1, that will render the right-hand side of the equation equal to 0. So now what we have to do is test different values, because we know alpha, we know X for the feed. So what we need to do is test the different values in order to find the root of the equation, and that's the theta value. Now this is a trial and error process, and again, if you want to access or have a downloadable spreadsheet that does it for you, let me know in the comments, and I'll see if we can make one for your reference if you want it. So again, let me know down in the comment section. So essentially what we need to do is take each of the variables that we have, and I've just constructed a table. So you have your XI, these are the feed compositions, you have your volatilities respectively, and then we just multiply these values together and we get this one here. Now I've tested the value of theta at 1.5, and what that's gave us here is it's gave us a summation of 0.564. Now remember, the right hand side of this equation is equal to 0. So we need this as close to 0 as possible. So that's not going to work. So if we try 1.3, then we've actually now went negative. So that means we need to try between 1.5 and 1.3. And in this case, we found that 1.35 was within a tolerable range. So what we'll now say is that theta for this particular system is 1.35. So that's the value that we'll take when we apply these equations. So now what we can do is, using the following equation, the other reflux ratio equation, we can now deduce what our min is. We can now find what the minimum reflux ratio is. So we have our respective values, they are from the tables before. We multiply these two together. We then include the 1.35 in the calculation. We take the summation, because remember, it's the summation of all these different components, because each component will have different properties, and therefore it will have an impact on the overall behaviour of the mixture. So we take the summation, and that tells us that we now have our min plus 1 must be equal to 2.42. That tells us that the minimum reflux ratio for this system is 1.42. So this has found another element of the question. Now, one thing to note is we could actually rewrite this type of equation in a more general sense, and this is needed for the next part. And the general sense equation is that we could say, based on this system, that R min divided by R min plus 1, because we know that that is equal to R min. So we can use this ratio for the minimum, but we can also use it for any reflux ratio. It doesn't have to be the minimum. But the reason we need that is because we now need to bring in the Erbar-Maddox correlation chart. And the reason we need that is so that this is the relationship between the reflux ratios and the number of stages. So if we use a reflux ratio now of 3, then what we say here is R over R plus 1, so 3 over 4 is 0.75. And then we have R min divided by R min plus 1, that's going to give us 0.59. So on our y-axis, we have R over R plus 1, so that's going to be the 0.75, that's our red line. Now our R min over R min plus 1 is 0.59, so that's these curved lines here. Now the point of intersection, what we do here is we now say that N min, that's our minimum number of stages, divided by the actual number of stages, becomes 0.74. That then tells us that our number of stages for a reflux ratio of 3 is 11.9. So there's a difference between the minimum, which was 8.8. Now you just repeat the same process, and we could test different values of R. So we go from 2 and we went up to 6. But what you can see is that as the reflux ratio increases, the number of trays decreases because there's more material leaving the column. The more material that is re-entered into the column, the more stages is going to be required. So now, in order for us to find the feed entry point, we're taking our reflux ratio as 3. So it is now important that we remember that the number of stages has to be a full integer. So we can't have 11.9 of a tray. So we round this up to 12. We could never round it down the way because it's not going to be enough. We need 11.9, so we round it up to 12. So that means our system involves 12 stages. Now we need to use the Kirkbride equation in order to solve this part of the question, and that's because we need to reduce the fraction of the light key and the heavy key in both the top and the bottom products. Now again, a lot of these correlations have topics all by themselves, and we look at these individually and in more detail in our distillation design course, a fully comprehensive distillation course, all the way up to ChemEng level. Again, I'll put a link in the description to that if you are interested. But here what we have is our fractions for our light and heavy keys in the bottom and the top products respectively. Now here, the 55 and the 45, these are the flow rates that you would have seen at the beginning of the question. And then we just need to bring in our equation that we've seen before. That's our Kirkbride equation for these, and then we use the equation for basically the feed point, and that's going to be this NS. That's the thing that we want. So we have all the information, we can populate that, and if we just tidy it up, we tidy this side up, the logs will cancel each other out, so we get NR over NS is equal to 0.91. Now, here's the thing that you need to remember, is that the minimum number of trays in those formulas counts for the reboiler. So that means in order for this to work, i.e. where the feed comes in, you have to neglect the reboiler. So in this case, NR is actually going to be 11, not 12. And we know that the reflux ratio in this case is 3. So what that tells us is we now have two correlations for the system, in that NR plus NS is equal to 11, and NR over NS is equal to 0.91. So now we can make them equal to each other, we can simplify the system, and we work out that NS is equal to 5.76. Again, it has to be rounded to the nearest integer, so in this case it's 6. And what that tells us is that the feed enters on tray number 6. And that's how you apply the full shortcut design equations for a multi-component distillation column design problem. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in understanding and applying the concept of the shortcut method. If you liked this video, please consider liking and subscribing to the channel. It really helps us reach as many chemical engineering students as possible. Thank you for your time, and we hope to see you in another video.